Okay, so this chapter is about temperature, and temperature tells you how hot an object is. Okay, so here let's look at this simulation. Okay, here's a gas. It's at 27 atmospheric pressure. Okay, the gas in this room is at 1 atmosphere. Okay, the temperature is 300 degree Kelvin. What does this temperature indicate? What does this tell you about the gas?
Average kinetic energy?
It's average kinetic energy. So you can see that every particle is not moving at the same speed. Okay, all those particles have different kinetic energies. The average kinetic energy, temperature is a measure of the average kinetic energy. Okay, so now let's say I warm the gas. If I double the temperature, okay, if you double the temperature, you're doubling the average kinetic energy per particle. Okay. Now here's an interesting fact. Okay, so there you can see the gas molecules moving about. You can see the temperature of the gas. Okay, I mean the temperature tells you the average kinetic energy. Okay, the temperature of the gas in this room and the temperature of this table is the same. What does that temperature mean there? The atoms are not flying around.
Type of matter.
I'm sorry?
Type of matter.
Yeah, no, but what does temperature mean there? So what's happening is, even though the atoms are fixed there, they're oscillating about their equilibrium position. And so that's the average kinetic energy. Okay? So temperature measures the average kinetic energy of each molecule. Later you'll learn temperature also, so these molecules have kinetic energy, they have potential energy as well. Okay? So when you add heat to a substance, the heat is equally distributed among all the degrees of freedom. Okay? All right, so temperature is related to the average potential energy as well, but average kinetic energy is easy to measure. Okay? All right, so that's what temperature is about. Okay? Now, the first 4 chapters in this course are from the subject of thermodynamics. Okay? Thermodynamics, for most of you engineers, that'll be an entire course. You'll do an entire course on that. Some of you engineers might do 2 courses on that, and most people don't like it, but if you listen carefully, it's actually interesting. Thermo, meaning heat, dynamics, how heat flows. Okay? Heat is the worst form of energy in the sense that, so if I have potential energy, I can convert 100% of it to kinetic energy. Okay. But let's say I have 100 joules of heat. In your car, you can convert 20% of that to the motion of the car. Okay, so in that sense, it's the worst form of energy. So when you have heat and you want to convert it into other useful forms of energy, the efficiency is less. Okay? So your car is 20% efficient. Okay? On the other hand, the motion of your car, when you apply brakes, what happens to that? All the kinetic energy is converted to heat. Okay? So heat to mechanical energy conversion is about 20% efficient, depending on your system. So the world's most efficient heat engine is about 40%, 40 to 42%. That's a thermal power plant. Okay. And mechanical energy to heat conversion is 100% efficient. Okay. So this, the first 4 chapters constitute the subject of thermodynamics. Okay, so here's a solid, and we already talked about this. Okay, so in a solid, the atoms or molecules are in fixed location, and what this picture is showing you is this end of the solid is hotter than this end. And what that means is these molecules are vibrating with a larger amplitude and their average kinetic energy is higher than these guys. Okay? So we'll study all these topics. There's a lot of slides in this chapter. I'll try and just give you the punchline on these guys, okay, on the slides. So thermodynamics is the branch which is concerned with heat and its relation to energy and work. Okay. A lot of times, why is it that we need energy?
To do things.
I'm sorry?
To do things.
To accomplish work.
To do work. Okay, that's why we need energy. Okay. So for instance, when I lift this object, I did work on this object. And what happened was I spent some energy and this thing gained energy. This thing gained potential energy. Okay? So you use energy to do work on an object, and when you do work on an object, you're transferring energy to that object. Okay? So when you use heat to do work, when you use heat to move your car, as we mentioned, the efficiency is low. Okay? So thermodynamics, we talk about all of that. Okay. The laws of thermodynamics are applied to systems which have many particles. Okay. What do we mean by this? So a thermodynamic system is a system that has many particles. What do we mean by that? 100 particles, 1,000 particles? I'm sorry?
All.
So a thermodynamic system is a system which has the number of particles are, we start talking about Avogadro number of particles. Okay? So generally a 50 particle system is not a thermodynamic system. Okay? A thermodynamic system has 10 to the power of 24 particles. Okay? That's what an Avogadro number is. So in this room, can you think of example of a thermodynamic system? What is a thermodynamic system?
The air conditioner.
The air in this room? Okay. The air in this room has about 10 to the 30 particles.
What we breathe out.
Yeah, so the air. This is a thermodynamic system. This is a thermodynamic system. The walls are a thermodynamic system. Here is a thermodynamic system. Okay?
Is that because they can be broken down to like Avogadro's number, or?
Well, I mean, that thing has Avogadro's number. One mouthful of water has Avogadro's number of molecules.
So what doesn't have?
So, okay, so if you think of the solar system, there's 10 objects, 10 particles.
Okay, gotcha.
Okay. You think of the pool table, that,
Yeah.
okay, so when you treat each of those pool balls as one particle, then it's a finite number of particles. Okay. So the laws of thermodynamics apply to systems which have large number of particles. Okay. So all these laws that we learn about will apply to all the systems here. Okay. So thermodynamics applies to a wide variety of topics. Okay. As an engineer, if you're a chemical engineer, aerospace engineer, mechanical engineer, cell biology, all those fields you need to know the laws of thermodynamics. In fact, they have even applied laws to economics and stuff like that. Now, here's the interesting fact. So this is a thermodynamic system. We'll consider the system in equilibrium. Okay. Now, this system is not quite in equilibrium. Why is this system not in equilibrium?
Because of us.
So we change.
No, because her surrounding is at a lower temperature and she's constantly losing heat. But
Yeah, so it's just because of our body temperature.
right. So Okay, but we'll consider systems in equilibrium. Okay, so we'll consider this gas essentially, which is not gaining energy and so on, even though we are losing heat, but we will ignore all of that stuff. Okay, so what is Avogadro's number again?
2 times 10 to the 23.
Yeah, so 10 to the 24 particles, and we have about 10,000 moles of gas in this room, so about 10 to the 28 gas molecules. Yeah. Every one of them is traveling at a different speed and so on in a different direction. But this system in equilibrium we'll describe using about a handful of parameters. So that's the amazing part. When somebody talks to you about this gas, they'll give you its pressure, its volume, its temperature, and that's about it. Okay? So we will use very few variables to describe the properties of these thermodynamic systems. Okay? So here are the 4 laws of thermodynamics. Okay? The 0th law just says that so this guy and this guy are at the same temperature. Okay? So all inanimate objects in this room are at the same temperature. Okay? Is this guy exchanging heat with this guy?
If it's in equilibrium or right now?
Well, I just said they're in equilibrium.
Oh,
Are-
They're technically always exchanging heat, but they're balanced.
Very good, very good. So they are, okay, so if they're in thermal contact, they are exchanging heat, but they're exchanging equal amount of heat. So there's no net exchange of heat. Okay? So they are in thermal contact and they're exchanging heat. Okay? Heat can be exchanged via 3 mechanisms. You might have heard of this: conduction, convection, and radiation. Okay? Now, the strength of the thermal contact might be, well, it can be strong or weak. Right now, the thermal contact via conduction is strong. Now, that got weak. Okay? So the strength of the thermal contact might change, but when you're in thermal equilibrium, there's no net exchange of heat. And when 2 objects are in thermal equilibrium, they're at the same temperature. Okay? The first law of thermodynamics expresses the existence of a quantity called internal energy, which is thermal energy, which is random, kinetic, and potential energy. So in this example, these molecules don't have potential energy. They have, assuming they're not charged. So thermal energy is the internal random kinetic energy of these molecules. Okay? And if you brought this gas in contact with another gas that was at a lower temperature, heat will flow from here to there. And heat is this internal random energy flowing from here to there. Okay? So the internal random energy for the hotter object will get lower, and the average energy per particle for those guys will get higher. Okay? So heat is this internal random energy. Okay? All right, so here is this box of chalk. The temperature of this box is 300 degree Kelvin. Okay, so that's a measure of the internal random energy. Now let's say I move this box at 10 meters per second. Did its temperature change? Okay. So internal random energy, temperature is a measure of the internal random energy. Okay. It's not related to this external velocity. Okay. The second law of thermodynamics expresses the existence of a quantity called entropy. Okay. of a system and states that the entropy of an isolated macroscopic system never decreases. Okay. So entropy is a measure of, it's related to the randomness in a system. Okay. So if entropy never decreases, that means if you let a system evolve, so for instance, if I had a hot cup of coffee here, and I set it here, what will happen to that hot cup of coffee?
Temperature reduced.
It'll cool down. So energy will move from this hot cup of coffee into the room. What happened to the total energy of the cup of coffee and the energy of the room?
Energy of the room goes up.
I'm sorry? Yeah.
Yeah.
So,
Positive, negative energy transfer.
right. So here was the cup, here was the room. And heat flowed from here to there. What happened to the total energy of the system?
Stay the same.
It stayed the same. Okay? The total energy of the system remained the same. It just got redistributed. Okay? And why did it get redistributed? Because when the temperature comes to equilibrium, this process happened so that the entropy was increasing. When will this process stop? It'll stop when the temperature becomes equal, right? And that's when entropy has reached maximum. Okay? So, this law of thermodynamics tells you that heat processes happen in nature where entropy is increasing. Once entropy has reached maximum, then that process will stop. Okay? So that's the second law of thermodynamics. And again, this is just giving you a brief overview. Each of those laws will devote an entire chapter to that. Okay? The third law of thermodynamics, okay, so here's what that implies. Okay, what is the temperature measure? What does the temperature tell you?
The average kinetic energy.
The average kinetic energy per molecule. Okay, let me cool this system down. What is happening? They're getting slower. What is the best I can do?
Make it so they're not moving at all.
Stop all of them. I couldn't cool it any further. That's when we realized there was a lowest temperature possible. Absolute zero. Okay, so you guys remember, you all know the Celsius scale. Okay, what is the temperature in this room? 20 degrees Celsius. Okay, I can cool the air here. I can decrease the temperature. I can decrease it to 0 degrees Celsius. What is the lowest I can go? Negative 273. You try and explain this to your little brother. Minus 273 degrees is the lowest temperature. That's an odd number. Okay, so that's where we invented the Kelvin scale. Okay, so we just call this 0 degree Kelvin. Okay, so that's how absolute zero was realized, when we realized that temperature was a measure of average kinetic energy, and the best you can do is stop everything, and that's absolute zero. Okay. The third law of thermodynamics implies that it's impossible to cool a system to exactly absolute zero. So the statement is you cannot cool any substance to absolute zero. Why do you think that's so?
It's how do you get particles to completely stop moving? Especially with gases, that's what they do,
You can shoot lasers at them and stop them.
Well, because they're avoiding interaction with other things.
What?
They're avoiding interaction with other things.
Yeah. Yep. Mm-hmm.
Heat always on the end of the system. Escape around. Escape around.
Yeah. So what heat will always find a way into the system. What you're saying is there's always something hotter that heat always will flow from something hotter to colder. Okay, so so restating that, you want to cool this to absolute zero. You got to find something colder for the heat to flow there. Okay, and if there's no object at absolute zero, so there's a loose way of saying this. Okay. And if you had something that was at absolute zero, heat flows in there, and this is no longer at absolute zero. Okay? So it's impossible to get to absolute zero. So here's a very interesting fact. Okay. You can go to UF, and they have, they used to call it microkelvin lab. Now it's probably a nanokelvin lab. Anyway, they have these big flasks where they cool samples about that big to nanokelvin. Okay, probably colder than that. So the point is, this could be the coldest spot in the universe. One of the coldest spots, you know. Imagine that, just 100 miles from here. Yeah. The coldest spot in the universe. Okay. Now, when you make the samples so cold, like our friend here said, you know, the problem is heat is always leaking in. This truck driving by the building is heating the sample up from the vibrations. So you got to earthquake-proof this building and all that. Okay? So there's a lot of interesting technology that goes on to into this kind of stuff. Okay? So anyway, so you can never get to absolute zero, but we do understand the concept. Okay? So temperature is a measure of how hot an object is. Okay? It's a measure of the average internal random kinetic energy per particle of the system. Okay? So here's just an interesting number. When the universe began 13.8 billion years ago, the temperature at the Big Bang was roughly 10 to the 39 Kelvin. Okay? Today, we are, so here's the universe. We are bathed in electromagnetic radiation, a microwave radiation, and the temperature of this radiation is 2.7 Kelvin, 2.73 Kelvin. Okay. So this is roughly the same microwave that that you use in your microwaves. So the temperature of that is that. Okay. Of course, life couldn't exist if the temperature was uniform in the universe. Okay. Life exists only in places where this is hot and this is cold. There's a flux of energy, and life harvests some of this energy to grow and so on. Okay. So this, for instance, in our local environment, that's the sun and that's the earth. Okay. So you have to have an energy flux for life to exist. Yeah. So when the temperature of the universe becomes uniform everywhere, then all life will be dead by that time. That's, you might have heard of the heat death of the universe.
So when entropy,
I'm sorry?
when entropy reaches maximum.
Right. Mm-hmm. See, if you come to class, you actually think. That's okay. No child voluntarily eats broccoli. They have to be made. Okay, thermal contact. Two objects are in thermal contact when they can exchange energy. Okay? The strength of the thermal contact can vary. So what all are you in thermal contact with in this room?
Air, table, chairs.
Everything. Okay. your strongest thermal contact is, of course, with your seat. Okay? How are you exchanging energy with the walls?
We're heating up the air around us, and then there's the.
No, so that's convective heat transfer, but you're also emitting electromagnetic radiation. Okay? So if you're not at absolute zero, you're emitting electromagnetic radiation and you're exchanging heat via electromagnetic radiation. Okay? So as long as you're exchanging energy with any object, then you're in thermal contact with the object. Yep.
Do sound waves carry thermal?
Sound waves do carry energy, so when I'm talking, I'm making your eardrums vibrate, but that's a small amount of energy.
So we heat.
I can't, if you're cold, I can't warm you up by just talking to you. Right.
So do we heat?
I can make you angry by talking to you.
We heat the walls through convection and radiation.
I'm sorry?
Do we heat the walls with convection and radiation?
Yeah. Okay, so you're in thermal contact with an object as long as you're exchanging energy with that object. Okay? Thermal equilibrium, when there's no net exchange of heat, then you're in thermal equilibrium and then you're at the same temperature. Okay? And that's the zero. So two bodies in thermal equilibrium have the same temperature. Okay? The zeroth law just states that if A is in thermal equilibrium and B is in thermal equilibrium with that, then they'll be in thermal equilibrium with each other. It's just stating that all three objects are at the same temperature. Okay? And again, I'm just going to I'm going to quickly, give you the punchline on each topic. Okay? On each slide. All right, so here's something I want you to do. Touch the table and touch the legs of your seats. Which one is colder? I'm sorry? The metal. They're exactly at the same temperature.
The metal just conducts the
It just, transfers the heat easier.
So you're all bad thermometers. So what's going on?
it's taking our heat away faster.
So you're not worried more about the temperature, you are more sensitive to fluxes of energy. Okay, you want to maintain a constant body temperature. Okay. If you're losing heat fast, that's worrisome. Okay. So that's what this guy says. Okay, I'll let you guys read that. So your backside, which is not a very good thermometer, actually you are not a good thermometer, is nevertheless very effective in telling you whether you're sitting on a cabin equipped with wooden or metal toilet seats. Yeah, so again, so you're sensitive to energy fluxes. So for instance, here's another example. Now it's cold, but let's imagine it's cold and there's absolutely no wind at all. Okay. If you stand there, it doesn't bother you as much. But if you get on a bicycle and ride in the same weather, then you feel colder. The wind chill makes you lose heat faster, yeah? Even though the temperature is the same.
The moving and pedaling the bike can also warm you up, right?
Yeah,
But then you have wind pulling down too.
There's a bigger difference.
yeah, you're losing more heat. Yeah.
Not like that.
Now, if you had a bicycle with a lot of friction, maybe you might win out on that battle. Yeah. But still, your body, you're losing energy, you're losing your bank balance, and that's what will worry your body. Well, all right, so what does temperature tell you? It measures the average kinetic energy per particle, okay? So you need to quantify that. You need to have scales to measure the temperature of an object. And here are three scales that we use. Okay. Now, to build any temperature scale, what you need is, well, to build a temperature scale, what you need is some physical phenomena that happens at the same temperature. Well, what do I mean by that? Okay, so for instance, ice point, what this tells you is you melt ice and you stick your finger in it and it feels cold. You can do this in New York, you can do this in Florida, you can do this at the North Pole, and it feels the same temperature. So this phenomenon happens at the same temperature. And by the way, you need to do this at 1 atmosphere. At lower pressures, it melts at a lower temperature. But, okay. So under similar conditions, ice will always melt at the same temperature. And you want to build a scale, call it anything you want. These guys call this 0 degrees Celsius. These guys call this 32 degree Fahrenheit. These guys call this 273 degree Kelvin. Okay. You find that at 1 atmosphere, water boils at the same temperature. Okay. You can do it today, 10 years from now, 30 years ago, it felt the same. Yeah. These guys call it 100 degrees Celsius, 212 degree Fahrenheit, and 373 degree Kelvin. And so you can see already, we already talked about this, these two scales are the same, the origin is displaced, that's all. Okay. This scale between these two physical points, there's 180 degrees and 100 degrees here. So these have more divisions, so this is a finer scale. Okay. So if you need finer temperature measurements, then you use the Fahrenheit scale, which is what we use. Okay. And why do we do that? Well, for this thermodynamic system, her temperature is 99 degree normal temperature. Her temperature goes to 100 degrees and she starts complaining. Okay. 1 degree change in temperature and you start complaining. All right, so in applications we need, some applications we need finer scales. Which one is hotter here? They're the same, yeah. How many temperature scales can you build? I'm sorry, as many as you want. Yeah. Now, for everyday applications, these two physical phenomena are good, but for more precise measurements, here are these two physical phenomena are better. Okay? Absolute zero, everybody understands, is when all molecular motion ceases. Here's a triple point of water. Anybody know what that means?
The triple point?
Oh.
Yeah, it's on the ridge of all different states of matter.
Okay, so for that, so you have to understand this phase diagram. Okay. This is a very important thing. So if you have a material, if you have a substance, okay, what this phase diagram says is, okay, so this phase diagram, again, you can have different parameters. It measures pressure and temperature. Okay. So what this tells you, this is for water, for pure H2O. What this is telling you is for this temperature and that pressure, this substance can only exist in the liquid state. So it'll tell you what physical state it can exist in. For this temperature and this pressure, it can only exist in solid state. So this diagram has a lot of information in it. Okay? So, that's a phase diagram. At this temperature and this pressure, it can only exist in vapor phase. Along these lines, what's going on?
It's going from ice to water.
It can, if you're on these points, you can have both ice and water. The two phases can coexist. Along these points, water and vapor can coexist. So next time you see a glass of ice water, you're somewhere on this line. In fact, you can be more precise. When you're sitting at a restaurant, what is the pressure? 1 atmosphere. So there you are. So that ice water is at 1 atmosphere and 0 degrees Celsius. Okay. Well, but the room is warmer, and so there's heat flowing in. But that glass of ice water is at 0 degrees Celsius. So what's happening to the heat flowing in? It's melting the ice. It's not raising the temperature.
It's going to reach
What?
equilibrium.
Right. So that system is still at 0 degrees Celsius. All the input heat is melting the ice, okay? All right, now I'll tell you one more little neat thing about this thing. Okay. So water is unusual. This is a negative slope, okay? So the coexistence of ice and liquid, for most substances, the curve will be like that. It'll have a positive slope. Okay. So here's an interesting consequence of this. Okay. What that means is, so for most substances, that would be true. So for instance, if this was not water, for instance, let's say you take some kind of liquid, let's say liquid ammonia, you increase the pressure on liquid ammonia, it would turn into a solid. But for water, you take ice, you increase pressure, and it melts. Okay, and that's what makes skiing possible. So let's say this is snow on the ground, and you get a device like this, stand on the device. What did you do? You just increase the pressure here. You increase the pressure, that ice melted, it's become water, that's become lubrication. And now you can ski away at 100 miles an hour. Okay. So anyway, you guys need to learn to appreciate these phase diagrams. You'll see these, many of these in your thermodynamics classes. And again, the idea is this, for substances, it tells you what kind of phase this will be in.
So, since water is like the only material that,
Mm-hmm. Has the negative slope. Yeah.
yeah,
Mm-hmm.
does it mean you can't ice skate on like solid?
Yeah, carbon dioxide. Yeah, dry ice. Yeah.
So you can't
Mm-hmm.
ice skate on dry.
I'm sorry.
So you can't dry
It's
can't
ski-
skate on dry.
Yeah. So you have to have a negative slope to skate. Yeah. Here's another thing you might have heard of: self-defrosting refrigerators. You guys heard of that? Nobody rich enough to have those kinds of refrigerators. Okay. Go ahead, Jeff.
Oh, I just couldn't hear what you had said.
Oh, there are such things as self-defrosting refrigerators. Okay, so here's how they work. So you see, this is if the pressure, and by the way, this is the partial pressure of water vapor. So if the pressure is below 0.06 thousandths of an atmosphere, that's the pressure of the water vapor in the, okay? You can go, ice can directly change to vapor. So these self-defrosting refrigerators, all they do is in the freezer, they reduce the pressure of the pressure of the water vapor to less than that, and ice will directly go into vapor phase. Okay. here's the triple point of water. Okay, triple point of water just means all three phases can coexist. Here's the vapor phase, here's the solid phase, here's the liquid phase. And this happens at precisely this temperature and pressure. And the neat thing about this is, from this point, if you go in this direction, you can convert it all into water. If you go in this direction, you can convert all that substance into solid, and here all into vapor. Okay. All right, so here's how we found absolute zero. You can take a flask like this, and you can start at 100 degrees Celsius. Let's say you can have 3 different amounts of gases. Okay, so 3 flasks, 1 mole, 2 moles, 3 moles. So this is 3 moles, 2 moles, 1 mole. And then you start cooling down the gas, and the pressure decreases, and you find that. So this is how we sort of discovered absolute zero. And the pressure goes to 0 at the same temperature. Okay, so this is extrapolated. Why does pressure go to 0?
It's not pushing on any,
While all motion stops, then pressure would go to 0. And that's how we discovered absolute zero. Okay. All right, so in common, there are these 3 temperature scales in common use. Okay, and so whenever we are doing thermodynamics, just to be safe, well, when you use all the ideal gas laws and stuff like that, the temperature needs to be in Kelvin scale, okay? But these formulas tell you how to convert from Celsius to Fahrenheit scale and from Celsius to Kelvin scale. To go from Celsius to Kelvin scale, all you need to do is add 273 to it. To go from Celsius to Fahrenheit, okay? So this is essentially 2. And then add 30 degrees to it. Okay? So if you have 20 degrees Celsius, 20 times 2 is 40. 40 plus 30 is 70. So 20 degrees Celsius is roughly 70 degrees Fahrenheit. Okay. Anyway, between these 2 formulas, you can convert from one scale to another. Okay, so here are some interesting temperatures that have been measured. The interior of the sun, the temperature is 15.6 into 10 to the power of 6 Kelvin. So here's an interesting fact. I believe, okay, I'm not exactly sure of the numbers, but 10 to the power 4 Kelvin. That's the center of the Earth. Okay. There's the sun. And I believe this temperature we know up to 10% accuracy. We know this better than 1% accuracy. All right. What I want you to understand from this slide is the following. Okay, so I want you to make sure we understand this. Okay, this hydrogen bomb, here's a hydrogen bomb, here's a bomb exploding. And at the center of the explosion, the temperature is about 100 million degree Kelvin. Now the question is, how do we know this temperature? How do we measure that temperature? Did somebody go stick their fingers in there? Yep.
can you measure maybe the size of the explosion? Can you use pressure from the high temperature?
So here's how we measure all remote. I can measure the temperature of the walls and stuff like that. I know the surface temperature of the sun. You guys have seen these thermometers where they'll measure the temperature of, your temperature without touching you. Okay, so here's how all those temperatures are measured. Yeah. We said that all objects emit electromagnetic radiation. Okay, so if you take a solid or a liquid, hot, solid, or liquid, um, they, all objects emit electromagnetic radiation. So this is what is called a black body spectrum, but a hot solid or a hot liquid approximates this, okay? And you see at any given temperature, so this object is at 500 degree Kelvin, 5,800 degree Kelvin, it will emit, so the wavelength, this is the wavelength of light, and this is the intensity of light. So at this wavelength, it's emitting that intensity. At this wavelength, it's emitting that intensity. And watch this. I'll change the temperature of the object, and the curve changes. So the curve is unique for every temperature. So you want to measure the temperature of that wall. All you have to do is have a sensor, measure the intensity for this wavelength, measure the intensity for this wavelength, measure the intensity for this wavelength. Okay? And fit the curve, and then you know the appropriate temperature. Okay? So that's how those thermometers work. Okay? And that's how you measure the temperature of a furnace. Okay? So you're measuring the intensity of 3-4 different wavelengths of radiation. Okay? And that's how we know the temperature at the center of the sun, and so on. Okay, it turns out that from the center of the sun, what you're doing is you're measuring the neutrinos, the temperature of the neutrinos coming. Okay? The neutrinos do not interact with any of this material. You can't measure the photon temperature. The photon temperature the photons are very garrulous. They talk to everybody on their way. Okay, so their temperature changes. You can measure the photon temperature from the surface of the sun, and that's how we know the surface temperature is 5,800 degree Kelvin. All right, so anyway, you have to be aware of that. Here are some interesting temperatures. This is relativistic high ion collisions, so the LHC, so they can take heavy nuclei and make them collide, and that mess will have a trillion degree Kelvin temperature. Okay, 1,000,000 times hotter than the center of the sun. Imagine that. Okay. All right, did you guys want a break? Or do you want to? All right, so let's pause.